So in this video we're gonna talk about let's talk about the atoms. So in the last chapter we discussed about the matter, and then we know that matter is made up of an atom. So atom is the ultimate unit of matter, right? They normally form all kind of matter. So in this slide we're gonna talk about what atom is made up of and what are the different subatomic particles you can find within the atom. So first let's talk about the structure of an atom. If you see over here, structure of atom is, this is your atom, and within the atom you have a spatial very condensed area called nucleus. Right, and then outside the nucleus you have empty space. Right. So within the nucleus or within the atom you can find 3 subatomic particles, and those subatomic particles are named as protons, neutrons and electrons. So each atom is composed of these 3 subatomic particles. So let me write the subatomic particles. Why they are called as subatomic particle? Because they are present within the atom. So if I ask you what are subatomic particles, they are proton, neutrons and electrons. So now let's see the picture that is given on the right hand side over here, which will be easily visible on the right hand side. That will help you to understand better. So this is an atom, and then within the atom you have this small area, spatial condensed very dense area called nucleus. And then within the nucleus you can find 2 subatomic particles out of the 3. Those are protons and neutrons. So you can find 2 subatomic particles, protons and neutrons, within the nucleus. And then outside the nucleus you will see an electron cloud, right? So all this area outside the nucleus is composed of electron clouds. If you can see the name over here, electron clouds. So what is electron cloud? Electron cloud is basically composed of electrons that moves rapidly in the almost empty space surrounding the nucleus, right? If you can see, they're all empty space outside the nucleus. So electrons are freely available to move in this empty space, right? And the electron cloud comprise most of the volume of the atom. So if you can see, this electron cloud which is present outside the nucleus mostly cover the volume of the atom. So now let's talk about a little bit more about all the 3 subatomic particles that we discussed on the last slide: proton, electrons and neutrons, and then what they are and what the charge, mass and the location of all these 3 subatomic particles within the atom. So the first one is proton. Proton is symbolized by a letter or a symbol by P, and then it has a charge of +1, and then the mass of 1.67 10⁻⁻24 (-24), and you can find that proton within the nucleus, right? This is the area you can find the proton. Then if we talk about the neutron, the second subatomic particle that we can find within the nucleus, normally symbolized as a letter small n, and it has a charge of 0. So that means neutron doesn't contain any charge, unlike proton which has a +1 charge, right? And then the mass of the proton is already given over here, and then I already told you where you can find the neutron within the nucleus. And the last of the subatomic particle, which is electron, symbolized by small e, and it has a -1 charge, if you can see over here. And the mass of the electron is 9.10 10⁻⁻28. But if you compare the mass of the electron with the other 2 subatomic particles, which is proton and neutron masses, if you can see clearly, the mass of the electrons is very negligible. It is so small that we usually neglect the mass of the electron whenever we talk about the mass of the atom altogether, because the electron mass is so small, right? So keep this in mind. And then where we can find the electrons, like we discussed, they are present outside the nucleus in electron cloud. So if you can see over here, like we talk about the masses of proton, neutron and electron, which is on the range of 10 to the power -24. So the individual masses of each of these subatomic particles are so small, chemists face normally a difficult time to weigh these atoms, right? Or work with these masses. So that's why chemists use a special unit to get the mass of these subatomic particle called AMU, which is called as or named as atomic mass unit. So we normally symbolize as AMU in a short form, right? So what is 1 AMU? 1 AMU is around, you can say, 1.66 times 10 to the power -24 grams. So based on these scale, we can say the mass of the proton in AMU is 1.007, neutron is 1.009, and electron is 0.000559. So if you again compare the masses of proton and neutron with the electron mass in atomic mass unit, if you can see this is very small. And like I said, the mass of the electron usually get ignored whenever we talk about the total mass of an atom has. Now let's talk about some of properties of the atom, like we already discussed, but let's talk about one more time. What's the mass? How we can get the mass of the atom? Basically comprised of the proton and neutron. Why not electron? Like I already told, the mass of the electrons are so small that it can be ignored. And what basically the volume of the atoms composed of is normally composed of by electrons, because most of the area of the atom are normally composed of electrons or the electron clouds. So that's why volume is determined by the electron clouds or the number of electrons that atom has. And then how we decide what's the charge on an atom. So charge can be, it normally determined by the number of proton and electron. We'll see how. So there are two kinds of charges. One is called positive charge. The second one is negative charge, right? So how the number of proton and electron normally decide which charge an atom will have. So for example, as we know, proton has a positive charge, electron has negative charge. But if I ask you why not the number of electron, then atom has determined the charge of the atom, because neutron doesn't have any charge, it has a zero charge, so it doesn't contribute anything to the charge of the atom. So that means if you have high number of proton and a small amount of electron, you will have a net charge of positive. For example, let's say if you have 5 proton and if you have 4 electron, what's the charge on an atom? So now you can see you have 5 positive charge, 5 proton means 5 positive charge, 4 electron means 4 negative charge. So what's the total charge on the atom? So 5 minus 4 plus 1. So that means you have 1 extra proton, means 1 extra positive charge. That's why the charge on the entire atom will be plus 1. Right? And then I hope everyone know that the same charge repel each other. If you have 2 positive charge side by side, they will repel each other, and opposite charges normally attract each other. Means if you have a 1 positive charge, 1 negative charge, like sitting side by side, they will attract with each other. They want to pull each other, right, towards each other. So keep this in mind whenever we are going to work with the charges. Okay, now we're gonna talk about the elements. So first we'll talk about what is element. An element is a pure substance that cannot be broken down into a more simpler substances by any kind of reaction, whether it's chemical or a physical reaction. So it is a pure substance, right? So for each element, scientist has provided a single letter code or a double letter code, or you can say symbol for each element, whatever we know right now. So for example, if I say hydrogen, H, so the symbol for hydrogen is a single letter symbol called H, which normally says it is a hydrogen, right? Similarly, we have C. C stand for a single letter symbol called carbon. But sometime in the periodic, sometime element can have a two letter symbol too. For example, Na. So whenever, and this is we call as, let's say, sodium. So if you can see, this is a symbol, the element symbol for sodium, and this is a two letter code. So that means the first letter is always an uppercase. The second letter for the same element should be a lowercase. Right, so keep this in mind. Sodium is capital N and small a, not capital N and small and the capital A or the uppercase A. This is not sodium. It's always like this. For example, one more example. If you see over here Ca, what is Ca? The first letter is a capital or the uppercase symbol. The second letter is a lowercase symbol. So this is calcium. Calcium. One more example is if you have C, O, so this the first letter symbol is a uppercase symbol, second letter is a lowercase, so this is cobalt, one of the element over here. This is your cobalt, Co. But if you have the same letter like C and O, now this is not cobalt anymore because the first letter code is a uppercase. If you can see carefully, this is also oxygen like cobalt, but this second letter is a uppercase letter too. So this is not cobalt anymore. This is carbon monoxide, means this element, this has two element over here, or two atoms of the element, carbon and oxygen. But over here in cobalt, this is single element, cobalt. But carbon monoxide is made up of two element, carbon and oxygen. And how would I know? Because the first letter is uppercase, second letter is uppercase. So keep this in mind whenever you reading the element symbol, so that you don't get confused between a different symbol, whether the particular element is just made up of one element compound or is a combination of many elements. Okay, so if you see over here carefully, Au, this is a gold. On the left hand side, this is a symbol of the gold. This is we call as atomic symbol. If you can see, this is the first letter is a uppercase, second letter is U is a lowercase. So we know this is a single element. Just specify gold. And if you can see over here, there is a special way of writing an element. The top, there should be like always be a number on the top and on the bottom. So the top number will normally tells you the atomic number of that element, and the bottom number in this case is 197. It normally tells you the mass of that particular element, right? So we're gonna talk about what is atomic number or mass number later on. So what is later on? So right now it's already saying you the atomic number is what is a number of proton that particular element has. So we're gonna talk about later a little bit more about the atomic number. And then atomic mass is the average mass of the atom of that element. right? So we're gonna talk about these two things later on. Okay, so now let's talk about the atomic number. What is atomic number? Atomic number is normally denoted by a letter called Z. Whenever you see a Z, that means we are talking about the atomic number. And atomic number is nothing, is number of protons. It normally gives you the number of protons, right, in the atom. So basically, if an element has 5 protons in the nucleus, that means it has atomic number of 5. If any element has 10 number of protons, that means that atomic number for that particular element is 10. Right? Then the second term that you're gonna use is mass number, and it's usually denoted by a letter symbol A. So whenever you see any A written, that means we are talking about the mass number. So mass number is number of protons plus number of neutrons. So you can say P, and neutron is N, you can say P. Right, so this is how you normally get the mass number. Right. So keep this in mind. For example, carbon is your 6 and 12. Right. So the top number will tells you the atomic number, like we just learned in the previous slide. The bottom number is normally a mass number. Right. So this is your mass number, and this is your atomic number. Right. So if I ask you how many protons, how many neutrons, and how many electrons this carbon 612 has, the neutral atom of carbon. So the 6 is the atomic number, and we know atomic number is what? Number of protons. So I can say proton is 6. How many electrons? Before we go to the neutron, let's talk about the electrons. As we can see, the atom doesn't have any charge, right? The charge is 0. So that means electrons also have to have a 6 electron, because proton is a positive charge, electron is a negative charge. So they has to cancel it out each other before an atom is neutral. That's why they are equal. Positive, same number of negative, same number of positive, right? So now let's talk about how we're going to figure it out the number of neutrons. So we can see over here in the mass number, we know the number of neutrons, right? So if we know the mass number, what is mass number? Number of proton plus number of neutron. So this bottom number is normally tells you the mass number. So out of this 12, 6 is your proton, because what is this? We only know proton is 6. So how many neutron this carbon has to have so that it becomes 12? So it has to have 6 neutron too, because if you put 6 neutron and combination is come out to be 12, right? So this is normally you can get the number of neutrons. Right. So let me ask you one more question on this. You have nitrogen 7 and 14. How many proton, how many neutron, and how many electron in this nitrogen? So the top number 7 is your number of protons, and we know number of proton is what? Number of atomic number. So this is 7, and proton is positive charge. So I'm just writing 7 positive. How many electron this nitrogen has? Nitrogen doesn't have any charge, it has 0 charge, right? So that means number of electron has to have the same number of charge, right? 7. Electron is also 7, because the charges has to be equal to become neutral. Positive cancel negative. And now how many neutrons? So this is your mass number. Out of the 14, we know number of proton already, which is 7. So how many neutron I have to add to make it 14? 7. Right? 7 proton, 7 neutron. Total is 14. So this is how you normally calculate the number of proton, neutron and electron for any element, a neutral element, right? Not any charge but a neutral element. So keep this in mind, how you're going to calculate number of proton, neutron and electron for an uncharged atom or a neutral atom. So now let's try to do some problem on all the topic that we just learned. So there's a problem that says fill in the blanks with the correct subatomic particle. So you have to fill out the tables with the correct name of the subatomic particle. So the first option says dash and dash are located in the nucleus of the atom. So which two subatomic particles are present within the nucleus? So the first one has to be proton or a neutron. The second one is neutron, because out of the 3 subatomic particles, proton, neutron and electron, only proton and neutron are located within the nucleus of an atom, right? B party says dash has a negligible mass. So out of the 3 subatomic particles, if you remember, I told you that electrons have the negligible mass because it has very less mass compared to the proton and neutron. Option C says dash have positive charge. So out of the 3 subatomic particles, which one has a positive charge? Proton, right? Symbol is P, charge is +1. So option D says that subatomic particle that has a negative charge. So only electrons. Symbol is E, and then charge is -1. Electrons. So final answer is electron. So this is how you normally answer if you have any this kind of problem, right? Okay, and then this is the same problem but with the answer already that we already discussed on the last slide, right? Which one is the correct answer? So this is an answer for the same problem. So now let's talk about one more question on this. The question says calcium atomic number of 20 is a major constituent of bone and teeth. How many proton and electron are present in the neutral atom of calcium? So if you know the time, it says atomic number of 20. What does it mean? What is atomic number? Atomic number is a number of protons. So I can say proton is 20, right? So if proton is 20, that means if you have a positive 20 charge, how many negative 20 charge you should have to make it a neutral atom? You should have a 20 negative charge, and then electron has a negative charge. So that means you have to have a 20 electrons in the same atom so that they become a neutral, right? So this is how you normally get how many electrons. Let's try the second one. What's the atomic number for these macronutrient element? So phosphorus, sulfur and chlorine. So phosphorus has an atomic number of 15. If you go to the periodic table, which we're going to talk about later on, you will see it's written something like this, P15. So this is your atomic number. Sulfur, you will see in the periodic table, 30 is 16 on the top. So the atomic number is 16. Chlorine, you will see C small l 17. So these are atomic number. If you remember from the symbol of the element, like I told you, the top number we normally tells you the number of protons or the atomic number. So this is why the answer is 15, 16 and 17. Okay, so now we're going to talk about the isotopes of an element. So we know that an element is made up of all the atoms, right? So for each element, let's say this is any element over here, and this element is made up of atoms. So all the atoms of an element should contain the same number of proton and same number of electron, but sometimes they might not contain the same number of neutron. They may have a different number of neutron. So isotopes are atoms with the same number of protons but with a different number of neutron present within the same element, right? So for example, this atom of the element, let's say, may have number of neutron, let's say 2. This might have a neutron maybe 3. So they are isotope of each other because they have a different number of neutron, but they cannot have different number of protons. So keep this in mind. You cannot change the number of protons for any given element atom. If you're changing the number of proton, that means you're changing the element, right? So keep this in mind. So let's get back to the isotopes one more time. So isotopes are atoms with the same number of proton but different number of neutrons, right? Or you can say isotopes are different form of the single element. So let's take an example. We have 3 isotopes for hydrogen. If we talk about hydrogen, so hydrogen has 3 different types of isotope. The first one we call as simple hydrogen. We say as, let's talk about over here, hydrogen, right? And the symbol of the hydrogen is H11. The second one is deuterium, DEUTERIUM, right? Deuterium. The symbol of deuterium, which is an isotope of hydrogen, is again hydrogen because this has the same atom, is 1, 2. And the third isotope is tritium. Symbol is same, hydrogen, because this is the atom of the hydrogen, but 1, 3. So what's the difference between the hydrogen atom in hydrogen, deuterium and tritium? Because they are isotope of each other. If you can see on the top number on each of the hydrogen, 1, 1, 1. So that means, what does it indicate? It indicates the atomic number. So each isotopes of the hydrogen has the same number of atomic number, means same number of protons. So they are not changing, but what is changing over here? So if you see on the bottom over here, what this number is, this is a mass number, right? The bottom number is your mass number. So in the hydrogen you have 1, in the deuterium you have 2, in the tritium you have 3. So why we have a different mass number, even though they belongs to the same hydrogen? They are isotope of hydrogen, you can say this thing. And then if you remember, what is mass number? Mass number is a number of proton plus number of neutron. So like I said, you cannot change the number of proton. So the hydrogen isotope has 1 proton. So how many neutron in this one? The top one. Number of neutron is 0. How many neutrons in the deuterium? So proton is 1. To make it 2, neutron has to be 1. For tritium, to make the mass number 3, we know the number of proton is 1. So the neutron has to be 2. So if you can see over here, each different isotope of hydrogen has the same number of proton or atomic number, which is 111. But what's the difference in there? The number of neutron. The top one has number of neutron 0, second one has 1, and the third one has 2, right? and that's why we call as they are isotope of each other, right? Let me give you one more time this definition. Isotopes are atoms with the same number of proton but different number of neutron. So this is how you normally figure it out, how many neutrons are different within the same number of isotopes, right, within the same isotopes of that particular element. Now let's take an example. We have three isotopes of carbon are given: carbon 12, carbon 13 and carbon 14. So why is given as carbon 12, carbon 13 and carbon 14? So in basically in isotope, what are different is the number of neutrons. So if the number of neutrons are different, so what's gonna change? The mass number, right? So each carbon has how many proton? 666, because you cannot change the proton number in any atom, but what you can change, the number of neutron, right? So for the isotopes for each element, normally you can write it down, the name of that particular element of that atom with the number, the mass number for that particular element, right? So carbon 12, carbon 13, carbon 14. So this normally shows you the mass number, because the time we see is carbon, we know the number of proton or atomic number should be 6. That's why it's not usually important to tells how many atomic number you have in, or how many protons number you have in that carbon, right? So that's why whenever you see something written like this, some name and then the number in front of it, that means they are isotopes. The mass number is the only change, or the number of neutrons are the only change, right? So let's compare these three isotopes of carbon. We know the atomic number is 6, because this is the number of proton 2, right? How many protons? 6. Mass number we already know is 12, 13 and 14. From here 12, 13 and 14, but you need to calculate how many neutron. So out of what is mass number? Mass number is proton plus neutron. We already know proton is 6, so how many neutron we have to get it? 12 plus 6 number of neutron, right? To get the mass number 13, we already know the proton is 6, so we have to have 7 number of neutron. Similarly for 14, we have to have 8 number of neutron. So if you can see carefully over here, so carbon has 3 different isotopes and they have different number of neutron. That's what their isotope is. This is how you normally get how many different type of neutron you have in the different isotopes of the same element. Okay, so now let's take one more example on this. So we are talking about iodine 125 over here. So like I said, whenever you see a name of that element and then just one number, in this case 125, we know this is one of the isotopes of many isotopes that is available in nature, right? So we are just talking about iodine 125, right? And how you normally write the isotope, whether you can write just the full name and then the mass number of that isotope, or just a single letter code for that particular element, or the symbol for that particular element and the mass number, right? You can write both ways. And then we have a special term called nucleus symbol. In nucleus symbol, you have to just write the symbol letter, whether it's a single letter or one letter code, and then specify the atomic number on the bottom and mass number on the top, right? So depending on, sometime different textbook use different method to write the atomic number or mass number. So always remember this thing, the bigger number out of the two that is given is always a mass number, and the smaller number out of the two is your atomic number. So don't get confused if this number get flipped, 53 on the top, 125 on the bottom. Don't get confused. Always remember that the bigger number is mass number, smaller number is your atomic number, right? And then from this iodine we know 53 is what? Your atomic number. That means how many protons you have in this iodine? 53. 53. How many neutrons you will have? So we know mass number is proton plus neutron. Out of the proton and neutron, we already know the proton, which is 53. How many neutron we have to add to the 53 to get the 125? So you have to subtract these two numbers, 72 neutrons. So this is how you normally calculate one more time how many neutrons you have, right? So keep this in mind, right, that we discuss on this slide. So depending on the problem that you might be solving in the quiz and exam, you will get something like this. So this, if you look at this table one more time over here, there's the same concept that we already discussed on the previous slide. This table normally tells you the nucleus symbol and the representation of the isotopes of carbon. So this is a nucleus symbol. So this is carbon, carbon, carbon. This is 12, this is 6. This 12 is your mass number, 6 is your atomic number, right? Atomic number, this is your mass number, right? So again, second isotope of carbon, 13, 16, 14, 16. So instead, so we don't, like I told you, we don't need to write 6 because each of the, like all the three are carbon, so the number of proton has to be the same, which is 6. So how you normally represent any isotope? We just write the symbol of that element and then write the mass number in the front, because we only know how many protons we have. Or you can just write the entire name of that element, carbon, in this particular case, and write the mass number in the front, right? So if you see something like written over here, carbon, iodine, hydrogen, so you always assume this is your mass number, and then because of the carbon, we know number of proton has to be 6, because you cannot change number of proton, right? So keep this in mind. So let's take one more example. So this is a table given and you have to fill it out, fill in the blanks over here. So the first column says the isotope name, second one is the mass number, third one is your atomic number, fourth is number of proton, number of neutron, the fifth one. So you have to fill it out accordingly for the element given, and if the element is not given, you have to figure it out what's the isotope name. So let's start with the first, barium 131. The time I see the name barium, I know the number of proton will be the same. So what should be the number of proton in barium? Is 56, the atomic number, right? What's the mass number? This 131, the number written in the front. This is your mass number. How many number of protons you have in this barium 131? Atomic number is equal to what? Number of protons. So it has to be 56. How many neutron? So what is mass number? Mass number is your proton plus neutron. We all know proton is 56. How many neutron we have to get this combination mass of 131, number of 131? So it has to be 131 minus 56. The answer should be 75. Right, so this is how you normally solve for number of proton. But if you see the second row over here, the isotope name is not given. So we have to figure it out what's the isotope name. But what is given? Atomic number is given right now, 80. Right. So if you go to the periodic table that we're gonna discuss later on. So if you go to the periodic table and see what's the atomic number, what's the name of that element that has the atomic number of 80, or whatever, whichever element has a proton number of 80. So you will see the name of that element is mercury. Mercury. Right. And then we know the number of neutrons is already given is 117. So if the atomic number is 80, number of proton has to be 80, because atomic number is same as number of proton, and the number of neutron is given 117. So what should be the mass number? Proton plus neutron. So this has to be 80 plus 117. So it's come out to be 197. So the isotope is 197, right? Mercury 197. So this is how you normally solve any problem asking for the number of proton, isotope name, or the number of neutron. Right? So this is the same problem that we discussed on the previous slide, so but you already have the answer, so this is just for your reference how we solved the same problem on the previous slide, right? We already solved it 56, 75, 80, 197. Okay, so now we're gonna talk about the atomic mass of the element. So how we're gonna calculate the atomic mass? So before we calculate, let's talk about what is atomic mass. So atomic mass of an element is the weighted average of the mass of all of its isotopes according to their natural abundance. So we know that element may have a different number of isotopes, so the atomic mass is the weighted average of all the isotopic masses of that particular atom of that element, right? And then what's their natural abundance, right? So basically what you need to know is like the atomic mass that is given in the periodic table is the weighted average. You have to take the average mass of all the isotopes given for that particular element. We'll see how we can calculate this thing on the next slide by doing some of the example, right? Okay, so now let's talk about how we normally get the average atomic mass like we discussed on the previous slide. To determine the atomic weight for an element, you need two quantity. First, the mass of that isotope in atomic mass unit. In this particular case, chlorine, we know the mass of that chlorine 35 isotope, right? Because chlorine is present as two isotope, chlorine 35, chlorine 37. We know 35 and 37 are the mass number. So the first quantity that you need to know is the mass for each isotope. So for chlorine, the mass is for each isotope in atomic mass unit, AMUs are already given, right? The second quantity that you need to calculate the average atomic mass is their natural abundance, right? So the natural abundance for chlorine 35 is given out of the 100%. Let's say this is your chlorine element. So within that element you might have chlorine 35, and you might have chlorine 37, right? So, and then this is your chlorine element, right? So within that element you might have many chlorine 37, chlorine 37, chlorine 37, chlorine 37, and just one chlorine 35. So that's what's the natural abundance out of the 100% of that element. How much percentage belongs to the chlorine 37 and how much belongs to the chlorine 35, right? And then you can apply the same concept with every element. So in this particular example, the natural abundance is given out of the 100% that making up the entire chlorine element. Chlorine 35 isotopes makes 75.76% of that 100%. Chlorine 37 normally make up 24.24% of the entire element of that chlorine, right? So the formula that we're gonna use is the mass of isotope 1 multiplied by the fractional abundance of that particular isotope plus mass of isotope 2, in this case chlorine 37, multiplied by fractional abundance for that particular isotope, and then plus, and then if you have multiple isotope for that particular element, you can just keep on adding and multiplying with their fractional abundance, whichever will be given for you. So let's try to solve this problem for chlorine 35 and 37. Use this formula that is given on the top, and then let's try to figure it out what's the average atomic mass for that chlorine element in atomic mass unit. So the average atomic mass, which is in atomic mass unit, is your mass of isotope 1 34.97 times 75.76%, which is 0.7576. So I can write this thing like this, 75.76, and what's this percentage mean? Means out of 100. If you divide, you're gonna get 0.7576, right? So that's why I'm writing 0.7576. not 75.76. So keep this in mind, so don't get confused and then just write 75.76. You have to divide by 100 because this is a percentage, then plus then the mass of the second isotopes times the percentage abundance, which is 24.24. again divide by 100 because this is a percentage. You're gonna get with 0.2424, right? This is very important. And when you multiply both of them separately and then add them together, you're gonna get 35.45 average atomic mass in the unit of AMU, atomic mass unit, right? If you can see clearly, was the average atomic mass 35.45. so this is more closer to chlorine 35 isotopes mass compared to the chlorine 37 mass, which is 36.97, almost 37. Why? Because chlorine 35 has higher natural abundance, means it is present in high quantity compared to the chlorine 37. So the mass of the entire element should be close to the chlorine 35 mass, atomic mass unit, because it's present in high. So the average should be tilted towards chlorine 35 mass compared to the chlorine 37. So you can cross verify your answer too. So this is how you normally get the average atomic mass for any element. If the mass of that element is given, mass of that isotope is given, or the natural abundance for that particular elements are also given. So now let's take one more example of calcium. Calcium has 4 naturally occurring isotopes, which is calcium 40, 42, 43 and 44. This is a mass number because they are isotope, they have different number of neutron, and because of a different number of neutron they have different masses. And the second columns normally tells you how much percentage abundance in nature each of them is normally present in. So the first question says which isotope is the most abundant on Earth. So we can see calcium 40 has 96.95 percentage of natural abundance out of the 100. So your answer has to be calcium 40. Right, this is the max, this is the highest isotopes you can find in nature compared to all other 3 isotopes. Which isotopes has the greatest number of neutron? We know each isotopes of calcium, whether 40, 42, 43 and 44, has the same number of proton, because you cannot change the number of proton. So proton plus neutron. So if it has the same number of proton, what is different? The different number of neutron. So calcium has proton of 20. To get 40, calcium 40 should have 20 neutron. I can write over here 20 neutron. Calcium 40 should have 22 neutron. Then calcium 43 should have 23 neutron because it is 43. 20 plus 23, 43. Calcium 44 should have 24 neutron. So out of the following, which one will have the highest number of neutron? The answer will be calcium 44. Higher the mass number, you will have higher number of neutron, that is different compared to the other isotopes of that particular element. So this is the same problem that we did with the answer. We already discussed about both the answer, calcium 40 and calcium 44, and why this is the correct answer. Right? But this is just for your review. What's the answer for that particular problems? So now let's talk about the periodic table. So whenever you open a textbook, you will always see something, this kind of table given in the front of the textbook or on the back of the textbook, which we call as a periodic table. So periodic table is a valuable list of all the non-elements organized so that groups of elements with similar characteristic are arranged together. So that means all the elements that has the similar kind of physical or chemical property are arranged together, right? So we're gonna see it how. So periodic table is arranged into a 7 horizontal rows. These are called horizontal, this horizontal thing we call as rows. This is a row. So how many rows you have? You have 7 rows in the periodic table, right? 1, 2, 3, 4, 5, 6, 7, and then you will have like 18 columns. What are columns? This is a long, these are columns, right? This is column from top to bottom. So you will have 18 columns that has a group number written on it. So that means this is 1A, 2A, 3A, 4A, 5A. These are the group numbers, right? And then you have 3B, 4B, 5B, 1B, 2B. So they have a different column with a group number. So the column in the periodic table we call as a group, or you can also say as a family, right? So column in the periodic table we normally call as a group or family. The rows, the horizontal rows, we call as the horizontal rows as period. So if I go to the second period, that means I'm going through a second row, something like this, a second row that has lithium, beryllium, boron, carbon. If I say I'm in the fourth period or fourth row, that is I'm going from potassium, calcium, scandium all the way to krypton, right? So keep this in mind, right? And then periodic table are also divided into several special group number or special name. The group 1 we call as a main group elements, right? So if you can see the tall big column, group 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A, they have a special name called a main group element. So if I ask you what is main group element, these are the main big columns, right? So how many columns you have in the main group element? 8 groups or 8 columns, right? 1A, 2A, 3A, 4A, 5A, 6A, and 8A. So keep this in mind. And each group we have a special name, or you can say special name is given for a couple of the main group element group. So group 1A we call as alkali metal. So group 1A, if you can see over here, we call the name as alkali metal. So it include hydrogen, lithium, sodium, potassium, Rbs, right? Rubidium, cesium, francium. Then we have group 2A. We have a special name called alkali earth metal or alkaline earth metal. So this is your group 2A. Then we have a group 7. If you go all the way on the 7th group over here in the main group element, we name this group as, or a family as, halogens. So if I ask you name any element from the halogens family, I can say this can be a fluorine, chlorine, bromine, iodine, right? Any element in that group. The last group, group 8A, we have a special name called noble gas element, if you can see over here. So make sure you know, if I ask you name any noble gas element, it can be neon, argon, krypton, anything in this group, right? So these are called main group element with a different name for each particular group. Then we have a group from 1 to 8, and if you can see the letter code B over here, so make sure you know the difference. Main group element has a number with an A group, right? 1A, 2A, 3A, 4A. Then we have a special group called start from 1B to 8B. This is your 1B, and then 1, 2B, 3B, 4B, 5B, right? 6B, 7, and 8B. And these groups normally include a special type of element called a transition element, right? And then within the transition element you have inner transition element over here. So these all are transition element. This is small rows, columns, and then if you can see, these are called inner transition element, right? So this inner transition element are placed after 57 atomic number and then 89, right? So this is how you normally read a periodic table. Okay, on the previous slide we already talk about the periodic table, what are the group number, what is rows, right? Rows are also called as period, how many period we have in the periodic table, what are the name of the group number, right? Group number A has alkali matter, group number 2 alkaline earth metal. We already talk about this thing, but the question is why the element are arranged in the manner it is in the periodic table. So the elements are arranged according to their atomic number. So all the elements in the periodic table you'll see are arranged according to increasing atomic number, right? So you start with hydrogen atomic number 1, then helium atomic number 2, then come back again 3, 4. So all are arranged according to their increasing atomic number, right? The lowest atomic number start with and then keep on increasing and then place the element. But the next question is why hydrogen, and then we have helium, and then after helium then we put lithium again on the group 1 element, and then after atomic number 10 neon. Why wouldn't I put like 11 someone in here? Why I came back, or scientists put the sodium again on the group number 1? Because the scientists have seen that all the elements that have the same physical and chemical property, they put every element in the same group. That's why lithium, sodium, potassium, rubidium belongs to the group 1, because they have the similar chemical and physical property with rest of the element in the same group, right? So these are the two things that you need to remember. First, elements are arranged according to their atomic number, means number of protons, right? The second thing is that we cannot change the number of proton for any element, because if we are changing the number of proton, we are changing the element. So don't change number of proton, because if you change, you're changing the name of the element or the symbol of the element, or you're changing the element, right? And the third one is all the elements in the periodic table are arranged in a group or a family that has the similar kind of physical and chemical property. So these are the three things that you need to remember from the periodic table. So so in the periodic table, element within a group normally exhibit a similar kind of chemical as well as a physical property. So I can say element within a group share a similar chemical or a physical property reflecting the periodicity of the periodic element. Means if any group, let's say this is any group, tall column, let's say this is 1A. So whatever element you have in this periodic table, all should have the same physical as well as the chemical property. So any element belongs to the same group should have a same physical and chemical property. That's why they normally put them together like a family. Okay, so now let's talk about the elements. So elements can be divided into periodic table into 3 different types. First one is metals, second one is non-metal, and the third one is metalloid. So in the entire periodic table, you can have either metal, non-metal, or metalloid. So we'll see where we can find the metals, where we can find the non-metal as well as the metalloid. So if you can see over here in the periodic table, this zigzag line, normally differentiate between metal and non-metal, right? So every metal which is on the left side of zigzag line we call as a metal. Those elements are metal. Any element that is on the right side of this zigzag line, this is a non-metal, right? Remember this thing, non-metal. And the element placed on each side of this zigzag line we call as a metalloid, right? So make sure you understand this one. So metals are normally found on the left side of this zigzag line, Non-metals are found on the right hand side of this zigzag line, and then element placed on the top and bottom of this zigzag line are metalloid, right? So if I say magnesium is a metal because it's placed on the left hand side. If I say manganese, Mn, metal. Potassium, metal. Sodium, metal. If I say chlorine, which is placed on the right side of this line, is chlorine is a non-metal. Bromine is a non-metal, right? If I say nitrogen, a non-metal. So this is how you can figure it out whether the given elements belongs to the metal category, non-metal, or a metalloid. So metalloids are boron, silicon, GeAs. So these element that is placed on the line are metalloids, right? You can see the coloring, the purple color or pink color as a metalloid. Now let's talk about some of the physical property of the metal and non-metal that we already know where you can find it out, the metal and non-metal in the periodic table. Now let's talk about some of the physical property, how you can differentiate depending on the physical property of metal and non-metal. So metals are shiny in nature, whereas non-metals are dull in nature. Metals normally exist at room temperature, except you have just one exception called mercury. Mercury is liquid at room temperature, right? This is like a liquid, but except mercury, all the metals are solid. So non-metal can be exit as solid, liquid, or gas at room temperature, depending on which non-metal you're talking about. Metals are good conductor of electricity, whereas non-metals are poor conductor of electricity. That means electricity cannot be passed through a non-metal, where metal can easily pass through electricity through it. Metals are flexible, when non-metals are brittle, hard, or soft, right? So these are some of the physical properties that make sure you remember it to compare the metal and non-metal characteristic. Now let's take an example and try to solve it. So the problem says state group number as well as the common name for these elements. So beryllium. So if we ask you beryllium, where you have beryllium? Beryllium is Be, and where it belongs to? It belongs to the group 2a, right? And what's the name of this group 2a element? Alkaline earth metal. So beryllium belongs to the group 2a, and the name of that group is alkaline earth metal. Similarly, iodine, symbol is Ai, where you can find I. This is your iodine. And which group number is this one? 7a, right? Main group elements. So group number 7a, and then what's the spatial name given for that group number? Halogens. So any element belongs to the 7th group are halogens. So then iodine is also a halogen. Then let's talk about the argon. Symbol is A small r. If you say this is your argon, Ar. So which group number this argon belongs to? 8a. This is the main group element, that's why the group number is 8a. And then what's the special name given for that particular group? Noble gas element. So this is noble gas element. The last, not the least, is nitrogen. If you can see over here, nitrogen is over here. Which group number nitrogen belongs to? 5a. But there is no special name for this group number, right? So that's why we normally write no name in common uses. So we usually say group 5a element, right? There's no special name like noble gas, halogens, or alkaline earth metal, alkaline metals. Nothing is given for that group number. Okay, so this is how you do this problem. Let's go to the next slide. Okay, so now we're going to talk about the electronic arrangement and valence electrons. So how the electrons are arranged within the atom and what are valence electrons. So let's get to the next slide. Okay, so now let's talk about the electronic arrangement. What are electronic arrangement? Electronic arrangement are the arrangement of electron within the atom, right? And we know the electrons are situated outside the nucleus. So we need to know how the electrons are arranged within the atom, right? So before we go into that, If I ask you why the element within the same group in the periodic table always have the same kind of physical and chemical properties. For example, if we have a group number, this is one of the group in the periodic table, 1A. What's the name of this group? This is alkali. We call that name as alkali earth metal. Right. So all the element that is present in group A, alkaline earth metal, should have the same physical and chemical property. That's why they are arranged within the same group, or you can say within the same family. So what normally determine the chemical properties of any element? So the chemical property of an element are normally determined by how many number of electrons that particular atom has. Right. So to understand the properties of the element, we must learn about the electrons that surround the nucleus. So we should know about the properties of the electron that surround the nucleus. Right. So the modern description of how the electrons are arranged within the atom normally consider that the electrons are not free to move anywhere. For example, let's say this is your nucleus. This is your nucleus. And then you have a lot of free space surrounding the nucleus. So according to the modern description of the atom, electrons cannot be moving around anywhere or wherever the electron is. They have a spatial area where they can move, or a spatial region, you can say. So if you can see over here, these are the spatial ring or area where electron can easily move. Right. So for example, if you have one electron, it can just move on this spatial area. Right. If you have multiple electron can just use these spatial area, which we normally call as orbit, or you can name this spatial area also as energy levels. Right. Because to revolve around the nucleus, electron has to have some energy, so this spatial area provide that energy. Right. So that you cannot find any electron between the different energy level. Right. So for example, this first circle normally denote energy level of 1, the second circle energy level of 3, second, the third one is 3, and then you can keep going on according to the how many number of electron that you have. So each energy level normally shows a spatial energy for that particular area. So that means the energy of the electrons are quantized. There is a spatial term called quantized. Means each electron can revolve in a spatial orbit or energy level. You cannot find any electron within the two different energy level in the empty free space. You cannot find anything in here. Right. And the second important thing is that if you go from the center of the nucleus towards outside, the energy of these level is keep on increasing. That means energy level 1 has less energy than energy level 2, has less energy than 3, and then keep going. So that means the last energy level will always have the highest energy compared to the energy level 1. So keep this in mind. So any electrons revolving on the first orbit of first energy level always have less energy. If they have less energy, they are more stable, right? More stable in nature compared to the electron that is revolving on the last energy level. It can be 5th, 6th, 7th, 9th, doesn't matter how many energy level you have. If any electron revolving other than 1, then that particular electron has higher energy than the electron that is revolving on the first orbit or first energy level. so we have different name, right? We also have a different name called principal energy shell. Principal shell. So don't get confused if you get different name, principal shell, energy levels, or orbits. It's like a same synonym name for the energy level, right? Okay, so we already discussed about this thing. Electrons can have only a certain allowed energy. Like I told you already, they cannot be moving around randomly across the nucleus, right? And then symbol N normally show you what's the energy levels, right? So if you have, so it normally shows with a small letter symbol called N. So if you see N written, that means it can be principal shell, energy level, orbit, both are same. Okay, so let's get to the next slide and see how the electrons are revolving around the nucleus. So this is just a visualization of electron energy level. If you can see on the left hand side, this is the lowest energy level, this is second energy level, third, fourth, and keep going on. You can keep, and if you see the difference between the energy level 1 and energy level 2, you will see the energy is always increasing, right? So energy level 2 has higher energy compared to the energy level 1, and then 3 has higher energy than 2, and keep going on, right? So this is one important thing. And then if you go to the picture B over here, it normally show you the arrangement of electron within the particular atom. So if we talk about hydrogen atom, how many electrons hydrogen has? Hydrogen has 1 electron, because the atomic number for hydrogen is 1, number of proton is 1. So that's why to neutralize the hydrogen plus 1 charge, hydrogen has to have 1 electron. So if you have 1 electron, where should the electron will go? Energy level 1, 2, 3 or 4, which one? Always the one, the smallest energy, right? Lesser the energy, more stable is the electron. So it doesn't go to the 2, 3, 4, it always goes to the first one. If you have helium, the second element on the periodic table, how many electron? Atomic number of 2, that means proton is 2, that means 2 positive charge, electron has to be 2 to neutralize that 2 positive charge. And if you can see, both the electron occupies the energy level 1. So why the second electron doesn't go to the, or you can say didn't go to the energy level 2? So we'll talk about this later on, why the second electron also goes to the first energy level, right? Then we have the element lithium, which has the atomic number of 3. That means 3 protons. To neutralize 3 proton or 3 positive charge, you have to have 3 electrons. So that means lithium has 3 electrons. So out of the 3 electron, 2 electron goes to the first energy level, and the second electron goes to the energy level of 2. So now the question is, why cannot I put the third electron along with the 2 electron that we put on the energy level 1? Why the third electron jumped to the energy level 2? So we'll talk about this arrangement later on, why the electron did jump to the second, or did place on the second orbit or second energy level compared to the 1, right? Because energy level 1 has the lowest energy, still the third electron goes to the second energy level. So we'll talk about this thing in the next couple of slides, but this is just an overview of energy level, right? So now let's talk about how many numbers of electrons you can put in each energy level. So let's say if this is staircase, this is energy level 1, this is energy level 2, this is energy level 3, right? How many electron I can put in the energy level 1? 1, 2, 3, 4, 5. So how would I know? So there is a formula that you need to know, that will tell you how many electron each energy level can accommodate, right? You cannot have more than that electron for that particular energy level. So for example, if you have just one energy level in the atom, the formula is 2n square. So n represent energy level, So the energy level is 1. I can use the formula 2 1 squared. 1 square is 1. 2 times 1 2. So how many electrons energy level 1 can accommodate? Only 2. And if you remember from the previous slide, I told you lithium has 3 electrons. So out of the 3, 2 electrons were placed on the energy level 1, but the third electron moved to the, or you placed on the second energy level, because energy level 1 cannot have more than 2 electrons. That's the reason we put the third electron on the second energy level. Right? If you have energy level of 2, let's say how many electron you can put. The formula is 2n square. N is 2. 2 square. 2 square is 4. 8. So maximum you can have is 8 electrons. So the second energy level can have maximum of 8 electrons. If you have more than 8, then you have to go to the third energy level, because second cannot allow it. If you're on the third energy level, 2 times 3 square, 2 times 9, 18. So the third energy level can accommodate 18 electron, right? But if you have more than 18, it should go to the fourth energy level. So this is how you can determine how many electron each energy level can accommodate within the atom. Okay. Let's talk about this table that is given on the slide. This shows the electronic arrangement of the period 1 and 2 element. So if you remember, what is period? Period is row, right? So in this particular table, we have the row 1 element and row 2 element from the periodic table. So row 1 has only 2 elements, hydrogen and helium. So atomic number is 1, helium has 2. So if the atomic number is 1, that means how many electrons hydrogen should have? 1 to neutralize the number of proton, because the atomic number is same as number of proton, P. So number of electron is 1, and where should that electron go? In the energy level 1 only. There is no electron, so nothing will go in second and third. Helium with atomic number of 2 means number of proton is also 2. How many electron this helium should have? 2, because to neutralize 2 positive charge, electron has to be 2. And then if you have 2 electron, if you remember from the formula 2n square, energy level 1 can accommodate 2 electron. So all the 2 should go to the energy level 1. There is no electron left. Helium with a 3 atomic number means how many electrons lithium will have? 3 electron, because 3 positive charge, you have 3 electron to neutralize it. So the first energy level can take only 2, and then the third has to go to the second orbit or second energy level. There is no more electron to go to the third. So if I ask you how many electron second energy level can accommodate? 8 electron. So right now you have just 1. If you have this energy level can accommodate till 8. So let's take an example. Let's say nitrogen. Atomic number 7. How many electron? 7. So the first out of the 7, first 2 electron goes to the energy level 2. How many left? 5. Then all the 5 can go to the energy level 2, because how many it can accommodate? 8. So 5 can easily accommodate in energy level 2. If you go to the neon, electron is 10, because atomic number is 10. First energy level can accommodate 2. How many left? Out of the 10, 2 goes to the energy 1, 8 left. So all the 8 can go to the energy level 2. Right? So this is how you normally do it. How you distribute the electron in the atom, right? Depending on which atom you're talking about, which element you're talking about, hydrogen, helium. Right? Now there is one more table on this slide. This also shows the electronic arrangement for period third element, means third row element. So third row element is, if you go in the row wise, on the third row you will see sodium, magnesium, aluminum, silicon, right? So we'll see how the electrons are arranged within these atoms. So sodium has an atomic number of 11. How many electrons sodium will have? 11. So out of the 11, the first one can take 2, second one can take 8. We know by the formula 2n square. for each energy level, and how many left out of the 11? 10 is already placed, then the 1 is left, and then there is no other space except n equal to 3. Right? Let's talk about phosphorus, atomic number 15. How many electrons? 15. The first energy level will take 2, second will take 8. How many left out of the 15? 10 is already used, 5. So all the 5 electron can go to the energy level 3. How many maximum number of electron the energy level 3 can hold? If you remember, 2 square, 2 times 9, 18. So it can hold at least 18. So if you can see, for argon 18 electron, 2 electron first, 8 electron second. How many left? 8. It can go to the third easily, because the maximum has a power of accommodating 18. So you are just putting 8. So it can easily go to the n equal to 3. So this is how you normally arrange electron in different energy level. Okay. So now let's talk about the valence electron and periodicity. What are valence electrons? So valence electrons are those electrons that are present in the highest energy level of an atom, or you can say those electrons that are revolving on the last energy level of that particular atom. Energy level. For example, if I have lithium, how many electron lithium has? 3 electrons, because it has atomic number of 3. So the first energy level can take how many electron? 2. Second energy level can take how many? 8. But how many left out of the 3? 1. So what's the last, or what's the highest energy level in lithium? It's 2, because after that we don't have any other electron. So this is the electron, the last electron in that particular atom that is revolving in the highest energy level, which is in this case is 2. So this is your valence electron. So lithium has how many valence electron? 1. Right, so remember, we'll do some more example in the next slide, but just remember this thing: electrons that are revolving in the last orbit of that particular atom, we call those electrons are valence electron. So what are periodicity? So periodicity is nothing, it's just like a repeating pattern found in the periodic table. So if you see in the periodic table, we'll talk about the periodicity when we'll talk about the periodic table later on too, right? But right now, what is periodicity? Is the repeating pattern found in the periodic table, physical and chemical property, and electronic arrangement. So you will always see a repeating pattern for a physical and chemical property as well as for electronic arrangement. This is called a periodicity. Right? We'll talk about more, but let's go to the next slide now. So now let's talk about the group 1 element, how to figure it out how many valence electron group 1 element has, which has the name of alkali metal. So these are the energy level on the left hand side. You can see N1, N2, 3, 4. So let's talk about the hydrogen one. How many electron you have? 1, right? This electron. So what's the highest orbit that electron is revolving in hydrogen? 1, because there is no other electron in any of the rest of the energy levels. So the valence electron is 1 for hydrogen. For lithium, and the number of electron is 3. Out of the 3, 2 goes to the energy level 1, third goes to the second energy level. Was the highest energy level that lithium electron in the lithium is occupying, n equal to 2. And how many electron? Just 1. So lithium has a valence electron Ve 1. You have 1 valence electron. For sodium, how many electrons? 11 electrons. Out of the 11, 2 goes to the first energy level, 8 goes to the second energy level, and the last one goes to the third energy level. So what's the highest energy level the last electron occupying? Energy level 3. So this is your valence electron, the highest energy level occupied electron, 1. Let's talk about the potassium. Potassium has 2 electron on the first energy level, 8 on the second, 8 on the third, and then 1 on the fourth. So this electron is the last electron which is occupying the highest energy level, which is 4. So if you remember, valence electron are those electrons that is revolving in the last orbit or last energy level. So the last energy level for potassium is 4, which has just 1 electron. So valence electron 1. So if you can see the trend, each element in the alkyl group, one element has how many valence electron? 1, 1, 1, 1. So this is a periodicity, right? Each element in the group 1 element always or will always have a valence electron 1, right? So now let's talk about the group 2 element, which is alkali earth metal. Let's see if each element in the group 2 element also has the same number of valence electron or not. So beryllium belongs to the second group. How many electron beryllium has? 4. 2 goes to the first, 2 goes to the second. What's the highest level that beryllium last electron are occupying? N equal to 2. So how many valence electron this beryllium has? 2 valence electron, because this is the highest energy level that the electrons are occupying for beryllium. Magnesium, 2 electron, 8 electron. The last 2 electron goes to the third orbit or third energy level. So how many valence electron? 2. For calcium, if you can see the last energy level for this particular element or atom, the last electron is occupying N equal to 4. This is the highest energy level. So how many electrons are revolving in the highest energy level? Only 2. So valence electron 2. So if you see a trend, for each element in this group 2a has a same number of valence electron, 2, 2, 2. So that's why all these elements are placed together in a group 2 element, because they have the same number of valence electron. And then to have the same physical and chemical property, you have to depend on the number of electrons, especially of valence electrons, right? In this case we have the same. So that's why all those elements in the group 2 elements are placed together as a family. So what about these? We know these green dots are the valence electron, but what about these yellow dots? We call these yellow electrons, which is present within the last or within the underneath the valence electron. We call all those electrons are inner core electrons, right? So how many inner core electrons beryllium has? 2. Magnesium has how many? 10. 8 plus 2, 10. Calcium has 8 plus 8 plus 2, 18 inner core electron, right? So all the electron except the valence electron comes in a category of inner core electrons. Okay, so now let's talk about is there any relation between the number of valence electron each element has depending on which group number that particular element belongs to? So always remember, if you see from the last couple of slides, we just showed you group 1 element, which is alkali metals, always have the 1 valence electron. Doesn't matter which element we are talking about, if all the element in that particular group always have a 1 valence electron. If you choose any element from the group 2 family, they will always have 2 valence electron. Similarly, by using the same trend, group 3 to group 7a, each element in that different group 3a, 4a, 5a, 6a will have the same number of valence electron, 3 to 7 valence electron, and group 8 has 8 valence electron. So what we learn from here, so group number will tells you how many valence electron you have. Group number equal to valence electron for the main group element. This apply for main group elements. So remember this thing. Okay. So let's take an example, how many valence electron each of element has, which is given on the right side of this slide. But before we solve this problem, let me tell you one more time that we discussed on the previous slide. I told you, right, the group number is always equal to, the number of valence electron is always equal to the group number, right? So any element in group 1, which is alkali, earth, metal, always have one valence electron. Group 2 always has two valence electrons. It doesn't matter, beryllium, magnesium, calcium, Ca, doesn't matter which element you're talking about, you will have two valence electron, means two electrons are revolving in the last energy level. Then we are not concerned about the transition metal, we are just concerned about the main group element. Group 3 always have a 3 valence electron. Group 4, 5 has 5 valence electron, 6 has 6 valence electron. Halogens family, which is a 7th group element, has how many valence electrons? 7, means 7 electrons are revolving in the last energy level. Then we have the last group, 8a, noble gas family. So any element in the noble gas family has 8 valence electron except helium. Helium has 2 valence electron. This is an exception. Okay, except helium, everything, neon, argon, krypton has 8 valence electron. Okay, so now let's try to do this problem which is given on this slide. If you talk about barium, how many valence electron barium element has? Let's pick where the barium is. This is your barium, Be. So barium belongs to the second group. How many valence electron this barium will have? 2, because it belongs to the second group. Carbon, let's see where the carbon is. Carbon is over here, belongs to the fourth group, 4 valence electron. Nitrogen is over here, it belongs to the fifth group, 5 valence electron. Chlorine belongs to the 7th group, halogen family, 7 valence electron. So this is how you can figure it out, the number of valence electron for each element depending on which group number or group that particular element belongs to, especially for main group element only, right? Okay, so let's do one more problem. It says complete the table. So you have to just complete all the fill in the blanks or all the column that is available to fill. So let's try to do the first row. So the atomic symbol is helium. He was the name of that element, helium, right? Helium was the atomic number for helium, 2. If you see the periodic table, you will see helium has the atomic number of 2, and the group number it belongs to 2a. If you go to the periodic table again, you will see He belongs to the 2a. What's the period it belongs to? Period 1, means row. If you go to the first column, first row, you will see helium on the right hand side corner. Number of N1 electron, how many electrons belongs to the energy level 1 in helium? So before we put the number, we should know how many electron helium has. Helium has 2 electrons total. So helium has 2 electron, energy level 1 can take how many electron? 2. We just learn about this thing. So both the electron will go to the energy level 1. So there is no available electron that can go to energy level 2 and 3, right? So let's go to the second row. So nothing is given, but what is given over here? The number of electron for each energy level is given for that particular element. Let's see how many electron. So energy level 1 has 2 electron, energy level has second has 8, energy level third has 8. So how many total electron you have in together for this particular element? So 8 plus 8, 16 plus 2, 18. So the atomic number should be 18 because this is a neutral atom, right? The time I write atomic number 18, if you go to the periodic table, I know atomic number 18 belongs to argon, Ar. So the name is argon. And then if we know that element name or symbol, I know where it is normally situated. It's situated in the group 8a. And then which period, which row number? out of the 7 in the periodic table, it belongs to the period number 3. If you keep on seeing group row 1, row 2, row 3, you will see all the way at the end group 3 has, or period 3 has argon, right? So how I did this problem, whenever nothing is given, always calculate the total number of electron. So in this case is 18. So that's what I know. If you have 18 negative charge in that particular element, how many proton or positive charge that particular element should have? 18 to neutralize the 18 electron, total electron. So if I know the number of proton, so I should know that number of proton is equal to atomic number. So atomic number is also 18. So this is how I got it. So make sure you practice this type of problem. So this is again the same problem but with the answer that we already discussed, but this is just for your review. It's exactly the same. We already discussed why this is 18, why 8A, everything we already discussed. So now we're going to talk about a special term called radioisotopes, and then we're going to talk about what is alpha and beta decay is. So let's get started with a new topic called radioisotopes. Okay, so now let's talk about the radioisotope. Before we talk about more about the radioisotope, let me ask you about this question over here. So if we're doing any chemical reaction, most of the time, how the chemical reaction work? What are the main things that involve in the chemical reaction? Is the number of valence electron. So only the valence electron, or the electron that is present in the valence energy level of the atom, takes part in the chemical reaction in most of the cases. But there's some reaction that doesn't include the valence electron or any electron, but they involve subatomic particle, proton, neutron, electron, proton and neutron, not electron, right? So those type of reaction that use these subatomic particle, proton and neutron, we call that reaction as nuclear reaction, because in this reaction only proton, the subatomic particle that is present within the nucleus, take part in the reaction, right? This is different than the chemical reaction that takes part because of the valence electrons, or the electrons revolving the last orbit, right? So what are radioisotopes? Before we talk about the radioisotope, we already learned about what are isotopes. Isotopes are the atom of the same element that have same number of protons but different number of neutrons. So we already talk about this thing. So in nature, most of these type of isotopes that are present are normally stable, but a large number of those isotopes of the given element are not stable, right? If somebody is not stable, they're gonna release some energy, right? They want to convert into a more stable isotope. So radioisotopes are the isotope which is unstable and spontaneously emit energy to form a more stable nucleus. So that means radioisotopes has an unstable nucleus, means the nucleus is not stable, and to become stable they have to release an excess of energy from the nucleus, right? So they undergo a decay to form a more stable isotopes, right? And this decay or this release of energy is spontaneous. It occurs spontaneously, right? And then the energy is released in the form of radiation. So we have a special term also called radioactivity. So radioactivity is a process, or is the nuclear radiation, right? The energy that is emitted in the form of radiation, nuclear radiation. So radioactivity is the nuclear radiation emitted spontaneously by an unstable radioactive isotope, right? So we have one more term called radioactive isotope, right? We also call this name as radioisotope. So what we learned, most of the isotopes are unstable, so they normally release energy in the form of heat or energy, and those energies released in the form of radiation called radioactivity. So now we're going to talk about what are the type of radiation normally get emitted when unstable isotope now converting into a stable radioisotope. So different form of radiation are emitted when a radioactive nucleus or radioisotope is converted into a more stable nucleus or a more stable radioisotope. That include three particles. One is alpha particle, beta particle, and gamma rays, and sometimes X-rays. So make sure these four are normally emitted in the form of radiation whenever an unstable radioisotope goes to a stable isotope or to make a stable radioisotope. Right? And we're going to talk about these things separately in the next slide. So less than 300 naturally existing isotope, 36 are radioisotope or radioactive. That means they radiate energy in the form of radiation. Right? And then all isotope with an atomic number greater than 82 are radioactive. So all the element that has, or all the isotope that has an atomic number of more than 82 are radioactive. Some are natural radioactive isotope and some are artificial, means man has made those isotopes that are radioactive. So let's start with the first particle that we discussed that release in the form of energy, which is alpha particle. Right? So alpha particle is a high energy particle that contains two protons and two neutrons. Two protons and two neutrons. So if alpha particle has two proton and two neutron, then that means that has a mass number of 4, atomic number of 2. Right? Okay. An alpha particle is normally symbolized by a Greek letter called alpha. So this is a symbol for alpha particle. Right? Or you can also denote the same alpha particle using an element symbol for helium. So depending on whether you see an alpha particle written as 4 and 2 or written in the form of an element called helium 2 and 4, because if you can see, you have the same number of proton and mass number, right? Like an alpha particle. So sometime book use alpha, sometime book use helium. So both has the same meaning, right? Okay. And whenever the radioisotope release a particle, in this case an alpha particle, then the new product or new element that is made, we call that element as a daughter nuclide. So remember these particular terms that we're going to use later on. So on this slide, we're going to talk about a special called nuclear equation, how we can use a nuclear equation to show the decay of any particle, whether it's alpha particle, beta particle, or gamma rays. We usually show in the form of nuclear equation. And what is nuclear equation? Like for a chemical reaction, we usually balance the number of atoms on both sides of the reaction. Similarly, in a nuclear reaction, we balance the mass number and the atomic number for the nuclei that's taking part in the reaction. So that's the difference between the chemical reaction balancing and the nuclear reaction balancing, where the nucleus is taking part, right? For example, if we take an example of an alpha decay, because we are talking about an alpha particle. So alpha decay is the loss of an alpha particle from the radioisotopes producing a daughter nucleide or nucleus with a mass number of 4 less than the parent nucleus or nucleide, an atomic number of 2 less than the parent nucleus or nucleide. What does it mean? So this is a nuclear reaction. Let's say over here, you start with the parent nucleus, whatever the nucleus in this case is radium, Ra, with a mass number of 223, atomic number of 88. After the alpha decay has happened, or after the nucleus release an alpha particle to get into a stable nuclide, we form a daughter nucleus or daughter nucleus, right? So the time you release, or the nucleus release an alpha particle, that means how many protons it release? It released 2 proton. And how many number of neutron it release? In this particular case, number of neutron 2, right? So whatever and then was the daughter nucleus is produced, Rn, with a mass number of 219 and the atomic number of 86. So what you see over here, in a nuclear reaction, remember this thing, whenever we balance a nuclear reaction, the mass number on the parent side always has to have equal on the product side, right? So let's say what's the mass number you have on the parent side. You started with 223. You release an alpha particle that has a mass number of 4. Then you are making a new nucleus with Rn element. Then the mass number is 219. So 219 plus 4 is equal to 233, right? So that means the sum of the mass number must be equal on both sides of the nuclear equation. Remember this thing. The second thing is the sum of the atomic number must be equal on both sides of the nuclear reaction. So in this case, on the left side of the nuclear reaction, you have atomic number of 88. On the right side of this nuclear reaction, you have to have the atomic number of 88, the sum. So the daughter nucleotide has atomic number of 86, alpha particle has 2, so 86 plus 2, 88, which is just as the starting point of the parent chain or parent nucleus, right? So let me tell you one more time. So in a nuclear reaction, nuclear equation normally written, which contain the original nucleus, new nucleus, or the radiation emitted. So in this case, original nucleus is Ra with 223, mass number 88, atomic number. The new nucleus that is formed is Rn with a mass number of 219, atomic number of 86. And then the emitted radiation in this particular case is an alpha particle, which has a mass number of 4, atomic number of 2, right? So in the nuclear reaction, you always see the sum of the mass number must be equal on both sides of the nuclear reaction, as well as the sum of the atomic number must be equal on both sides of the nuclear reaction. So you have to just check these couple of things whenever you make any nuclear reaction. So let's try one more example on alpha decay. The problem is saying write the balanced nuclear equation for the alpha decay. We know what is alpha. Alpha is 4, 2, mass number 4, atomic number 2 of an element radium 226. The time I know the symbol of the element Ra, I know the atomic number from the periodic table is 88. And what is 226? This is an isotopes of radium with a mass number 226. Right? So one is decay. To get into a more stable form, it released an alpha particle, and by releasing alpha particle, it decreasing the mass number by 4, atomic number by 2. So out of the 226, 4 is released, you left with 222. 88, out of the 88 atomic number, 2 was released in the form of alpha particle, left with 86. So the time I see the 86, I know this element is Rn. So this is how you normally make a nuclear reaction, right? You balance it, nuclear reaction. And let's compare whether the nuclear reactions are balanced or not. So how you balance it? You have to see the sum of the mass number must be equal on both sides of the nuclear reaction. What's the mass number over here? 226. In the product side, what's the mass number? 222 from here plus 4 from here. So 222 plus 4, 226. So that means mass number is balanced on both sides of the nuclear reaction. Let's say what the second rule says, the sum of the atomic number must be equal on both sides of the nuclear reaction. So let's say on the left side of the nuclear reaction, atomic number is 88. On the right side, on the product side, the daughter nucleus has an atomic number of 86. Alpha particle has 2. So total is 88, which is equal to the parent nucleus. So that means this nuclear reaction is also balanced, right? Which is doing an alpha particle decay. So this is how you balance it any nuclear reaction. So now let's talk about the second type of radiation that is released whenever the radioisotope decay into a more stable isotope. So we already talked about the alpha decay. Now let's talk about the beta decay, the second form of the decay radiation. So beta decay is normally a release of a beta particle. And what is beta particle? Beta particle is a high energy electron particle, and usually show with a Greek symbol beta, -10. So that means the mass is 0, mass number, and it has a charge of -1. Or you can also write a beta decay or beta particle in the form of electron, because this is also a high energy electron. So you can just write E -1. So both are same depending on whichever you can see in the exam or quiz or anywhere in the book. So don't get confused whether it's beta -10 or electron -10. They have the same thing, right? So what happened during the beta emission or beta decay? So during beta emission, one neutron, 10, is going to convert into a proton, 1 plus, and what you're gonna get? You're gonna get beta decay. So whenever you have a beta decay, what's happening in here? The neutron in the nucleus is converting into a proton. So that means during beta decay, the mass number is not going to change because if you can see, the mass number is same in proton and neutron, but the atomic number is going to change or increase by 1 in the daughter product, because neutron doesn't have any mass, but when the nucleus release a beta particle, you're gonna form one more proton. That means you are increasing the mass of the parent chain by 1, the atomic number of the parent chain by 1, not the mass number. Okay, so we'll take one example, but what's the main thing that you need to remember is beta particle is a high energy electron. Remember the symbol. And during the beta decay, you are not changing the mass number in the daughter nucleus or in the product, but you are changing the atomic number by 1. That means you are increasing the atomic number by 1. So let's take an example on this beta decay. So let's try to make one nuclear equation for the beta decay. For example, phosphorus with a mass number of 32, atomic number of 15. Whenever the phosphorus decay, a beta particle from its nucleus is going to convert into a sulfur. So what's happening over here? We know beta particle is 0, -1, no mass number, and a -1 charge. So to balance the nuclear equation, you have to make sure the sum of the mass number on each side of the nuclear reaction are same, as well as the atomic number, the sum of the atomic number on both sides of the nuclear equation are same. So let's start with the mass number. On one side of the nuclear reaction, mass number is 32, on the other side is 32, plus 0, that means 32. No change, so that means that's right. Let's see about the atomic number. It has to be same too. So before the nuclear reaction, the atomic number was 15. After that reaction happened and release the beta particle, then you got sulfur with an atomic number of 16. But if you see, the sum is 16 minus 1, because 16 plus negative 1 same as 16 minus 1, which is 15. So that means this is also same as parent atomic number. So that means the sum of both atomic number as well as the mass number on the nucleic equation on both sides are equal. So that means this reaction of beta decay are right. But if you can see over here, the phosphorus element during this decay is converted into a sulfur. Why the element change? Because the number of the number of protons has changed, because before the proton is 15, right now proton is 16. So I told you, whenever the number of protons change, you are changing the entire element. The element is not the same anymore because you are changed, right? So this is how the beta decay nuclear reaction work, right? Let's take one more example. It says write the nuclear reaction for decay of gold 198. The time I see gold, symbol is AU, I know I can go to the periodic table and figure it out what's the atomic number for gold, which is 79, and then the isotope is 198, which that means the mass number of that gold isotope is 198. And then it says using a beta emitter, right? If this gold particle emit a beta particle from its nucleus, what should be the daughter nucleus element is gonna form? So this is the time you release a beta particle with 0 and negative 1 charge, 0 mass. That means the atomic number is gonna increase by 1, right? That's how whenever you add negative 1 and 80, you will get 89. And we know whenever the beta particle release, the atomic number will get increased by 1. So the time I know is the atomic number is 80. And then if you go to the periodic table, 80 is mercury, right? So I know the element name. And then the sum of the mass number on both sides of the nuclear reaction has to be the same. So this is 198. And then the product side is 198 plus 0 is 198. So which is same as this side. Let's talk about the atomic number. We have 79. On the reactant side, let's say in the product side of the nuclear reaction, you have 80. And if you add negative 1, you're gonna get 79. So that means sum of both atomic mass number and atomic number are same. So that means this nuclear reactions or equation are balanced and right. So now we're gonna talk about the half-life. So if I ask you how fast do radioactive isotopes usually decay, so it depends on the isotope, right? So different isotopes usually decay at different rate, and the radioisotope decay is exponentially. They usually decay exponentially, right? And then the term half-life, that is very important. And the decay of isotopes is you usually define as half-life of a radioactive isotope is the time it takes for 1/2 of the sample to decay. So how much time does it require for 1/2 of the sample of the original parent sample to decay, right? So that means, let's say if you start with 4 particle, how much time does it take to decay this 4 particle into a half? So that's your half-life is the time. And then how much time does it need to convert 2 particle into 1 to decay into a half? So this is second half-life. So this is normally we see what is the half-life means, right? So let's take an example to visualize the half-life. You start with 24 particle of any radioisotope, right? You have 24 particle. After how much time? Let's say after 1 t half. So what is t half time? Means out of the 24 particle, how much time does it take to convert that 24 particle into a 12 particle? So that's your half-life. And then after another half-life, the particle number is going to convert from 12 to 6, half of it, right? And then another half-life, 3 particle, right? And then keep going on. So for after each half-life, you will get half of the number that you started with, right? This is how you normally define a half-life. So take one more example of half-life. Let's say iodine-131 isotope, radioisotope, has a half-life of 8 days. That means after every 8 days, the amount of the iodine-131 isotope just left half of the original one, right? So let's start. If we start with 100 grams, so after 8 days, how many grams are left, or how many grams is left? 15 grams. After another 8 days, so that means total of 16 days, 25, half of it. And after another 8 days means 24, 20, half of 25 to 12.5 remains. So this is how half-life work. So there is an alternate approach that you might use, or you can use, to determine how much amount of the product, how much amount of the sample left after like certain amount of half-life, right? The formula says n equal to 1/2 of n, small n. So capital N is normally denote the fraction of isotopes remaining, how much fraction of the particular isotopes remain after certain amount of half-life. And n, small n, is the number tells you how many half-life that have passed, right? Let's take the previous example. You started with 100 grams and then you used 3 half-life, right? After first half-life, you left with 50 grams, and then was the half-life 8 days. Another 8 day, 25 grams. Another 8 day, 12.5 grams, right? That we learned in the previous slide. So this is first half-life, this is second half-life, this is third half-life. So how many total half-life like passed to get this 12.5? 1, 2, 3, right? If we use the formula n equal to 1/2n, so 3 is the number of half-lives that we use. So that means 1/2, you'll get 1/8, that is 0.125. This is the fraction of the isotopes remaining, right? So what's the starting number? You started with 100 grams. This is the fraction that remains. So if you multiply both of them, you're gonna get how much amount is remaining. 12.5 grams remaining is exactly the same number that we just discussed on the previous slide. So it's depend on you which technique you think is more easy. You can do it both ways, right? So let's take one more example based on half-life. So the half-life of a cerium, one of the isotopes, 141, is 32.5 days. So that means T half. So every 32.5 days, the amount that you started with just become half, right? For 110 grams sample, how many grams remain after 3 half-lives? So that means how many half-lives we need to consider 3 half-life, and how many days must pass. So let's do with both the ways that we just learned, right? Let's start with the first one. You started with 10 grams, you have 3 half-lives. So after first half-life, how much amount left? Half of the previous one, 5. After second, 2.5, half of the 5. After third half-life, half of the previous one, 2.5, 1.25. So this is the amount that's left after 3 half-life. And it says how many days must pass. So that means what you need to do, you have 3 half-life, you can just do 2 ways, 32.5 plus 32.5 plus 32.5. So how much is gonna be? So it's gonna be 97.5 days. Right, so this is one way of doing. Just add all the three half-lives. That will give you the total number of days in those three half-life. Second, I can use a conversion factor. I can say one half-life is equal to our 32.5 days, right? And then how many? So I can make a conversion factor. I need days, so days has to be on the top. How one half-life is on the bottom, and how many half-life given? 3 half-life. So half-life is gonna cancel. Just multiply 3 with 32.5, you're gonna get 97.5 days. So it's depend whether you can add or you can use a conversion factor to figure it out how many days. So this is how you normally do the problem, depending on the half-life. Now let's use the second way that we learn using a formula. So the formula says n equal to 1 by 2 small n, right? So small n is what? 3 half-life is the number of half-life. So put 3 on the top, is 1 by 0.125. This is the fraction of the sample that's remain after 3 half-life. So when you started with 10 grams, so this is the fraction left. So multiply both of them, you will get the amount left, 1.25. This is what we got when we did the first in the previous slide, right, using the first method. And then again, half-life is gonna be exactly the same formula, 97.5 days. So it's up to you which method you're gonna use to figure it out, the amount of sample remain after a certain half-life, or how many days is gonna be in total half-life. But you can use both of them. Now we're going to talk about the high energy electromagnetic radiation. What are electromagnetic radiation? Because like we already know, in radioisotope there are certain type of energy release in the form of particle like alpha particle, beta particle, but we haven't learned about till now the gamma and x-rays, right? These are also the byproduct of the radioisotope decay. So alpha X-rays and gamma rays is a type of electromagnetic radiation that is released in the form of energy. So before we go further, let's talk a little bit about what are electromagnetic radiation, and then we'll go forward about the gamma radiation later on. So what is electromagnetic radiation? So electromagnetic radiation, normally also called as a light, this is a form of energy that travels through a space with a speed of light, right? Which is basically 3 times 10⁸ meter per second. Right? This is a speed of light, and then all the electromagnetic radiation travels through space with this speed, right? And there are different types of light waves in electromagnetic radiation. That is different because they have different wavelength. And then if we talk about what is wavelength is the distance from the top of one wave crest to the next. So that means if this is a wave, so this is a wavelength, this is your crest. This is your wavelength. Right, from one crest to the consecutive crest, that's your wavelength. The symbol of wavelength is lambda, right? So we're gonna see an electromagnetic spectrum in the next slide and see how many different types of electromagnetic radiation we have. So this is a way, normally this is a show, like a visualization of the electromagnetic spectrum, which is basically nothing, it's just the entire range of wavelength of all the light waves that are present, right? And then this is normally known as electromagnetic spectrum. So we have different electromagnetic rays called gamma rays, X-rays, UV light, visible light, infrared light, microwaves, and radio waves. And the energy of these waves, all these waves are related as inversely proportional to the wavelength of these waves. That means the lower the wavelength of any particular wave, higher the energy of that particular wave, right? So this is the sequence of increasing wavelength. It's the 10⁻²2. These are increasing. So if the waves are increasing, wavelength are increasing from left to right, that means the energy is going to decrease from left to right. That means the higher energy is always on the right hand side, in the left hand side on this electromagnetic spectrum, because it has the lowest wavelength, and the lowest energy is present on the right side of this electromagnetic spectrum because it has the highest wavelength. And we only know energy is inversely proportional to the wavelength. Higher the wavelength, lower is the energy. So that means out of the following electromagnetic rays or radiation, gamma rays has the highest energy and the radio waves has the lowest energy, right? And then you have at the center, you have the visible light too, that we can see with eyes on Earth, right? This is the wavelength for the visible light, 400 to 700 nanometer. And like we already discussed in the previous slide, the energy and the electromagnetic spectrum, how they are related. Energy of the light is inversely proportional to the wavelength. We already talked about this thing. That means longer the wavelength, lower is the energy. Shorter the wavelength, higher is the energy. Like they are opposite. And we know that higher energy, that means those rays that have the shorter wavelength can cause biological damage. So they are in so high energy, if it's stuck with the biological sample, it might damage that sample. There's some ionizing radiation that can also dislodge valence electron. Some of the example of ionization radiation is gamma rays, X-rays, or higher UV rays. All these radiation can damage biological sample when they come in contact with it because of its high energy. So now we're going to talk about those radioisotope that normally emit gamma rays. That is a symbol of gamma with 0 mass number, no mass number, and no atomic number. That means whenever the gamma rays release, it doesn't change any atomic number or mass number of the parent nuclei, because this is a form of energy, not a particle. So this is an important difference between the beta particle and alpha particle from gamma rays. So most radioactive decay include gamma rays, right? So most of the radioactive decay that's happening, including some beta particle or alpha particle, always release gamma rays as a side product, right? So whenever any nucleide, parent nucleide, release a beta or alpha particle, the daughter nucleide initially may be produced in an excited state. The nucleus is gonna be an excited state, means higher energy. And then we call that excited state as metastable state with a symbol as small m. So to convert that high energy state of the nucleus to a more stable energy state, nucleus or daughter nuclei release a gamma rays that forms a more stable state of the nucleus, right? So let's take an example of gamma ray emission, gamma decay of metastable technetium 99. So this is an isotopes that has a mass number of 99 and a symbol is Tc99, and this small m tells that the nucleus of this isotope is a metastable state, means it is right now in a excited state. So to convert from excited unstable state to a stable state, this isotope normally release gamma particle, right, using a radioactive decay. So the 99m, this m normally tells this is the nucleus of this isotope is in metastable state, higher excited state. So this convert into a more stable isotope, and then release a gamma particle. If you see, gamma particle doesn't have any atomic number, mass number, so it doesn't change the mass number and atomic number of the isotope. It just makes the isotope a more stable isotope, right? So remember this thing. So whenever you see a small m written in front after the mass number, that means that particular isotopes is present in the metastable state, and it has to release a gamma rays. Now on this topic, we're gonna talk about the penetration power and the biological effect of the radiation. How does the radiation affect the biological sample depending on the penetration power of that particular radiation? So now we're going to talk about what is ionization radiation. So ionization radiation contain a sufficient energy to dislodge valence electron, and so that means they are so much high energy, and that include all of them: alpha particle, beta, gamma, x-rays, and high energy UV rays. All are part, or all are example of the ionization energy, because they have high energy. And because of this high energy, whenever they come contact with the biological sample, it might lead to a mutation, because it might change the DNA, it might break the DNA, it brings some changes in the composition of the DNA, and this change in DNA called mutation can affect rapidly into a reproducing cell, so the damage is long lasting. So now let's talk about the factors that might affect the biological damage from the radiation. So there are two factors that depends how much damage that particular radiation or ionization radiation can cause to a biological sample. The first one is energy of the radiation, how much energy that radiation has. Second one is your penetration power of that radiation. Means, what is penetration power? Means the measure of the extent to which a particular type of radiation passes through a matter, right? How much distance that particular radiation can pass through a matter. That's your penetration power. So if you see from here, if you can see the alpha particle, we're going to talk about each of them separately. What's the energy of the particle and what's the penetration power for each of them: alpha, beta, x-rays, and gamma rays, right? So let's go to the next slide. So let's talk about the penetration power or the energy of the alpha particle. Alpha particle we know is high energy particle, but they are large and slow moving, right? Because of the mass number or the mass of the alpha particle. And because of the large and slow moving, it has a very little penetrating power, right? Even though it's high energy, but because of the masses, it has less penetrating power. So even the skin or a piece of paper can stop the alpha particle, but this alpha particle is very or extremely dangerous if it's ingested or inhaled, because even though it doesn't has a little penetrating power, but when it comes in contact with a delicate internal organ, it might cause a damage to that sample of the internal organ, right? So that's why it's extremely dangerous if you inhale or ingest any alpha particle. Let's talk about now the beta radiation. We know this has less energy than alpha particle, but the important part is it is much lighter than the alpha particle, and because of the mass is much lighter, it has much more penetrating power than the alpha particle. It can penetrate the skin, and it can also cause damage due to the greater penetrating ability, right? So this is way dangerous than the alpha particle. So if you see on the picture on the right side, that means a specialized heavy clothing or a thick piece of aluminum is required to stop the beta particle. If you can see, the aluminum can stop the beta particle. Now let's talk about the effect of gamma and X-ray rays. Both of them has less energy than the alpha particle and beta particle, but The important thing is the penetrating power of both of them, X-rays and gamma rays, are much more than the alpha and beta particle, and because of this more penetrating power, these two are potentially far more damaging than beta and alpha particle. Right? And then it has many uses in some medical application. And if you can see from the right hand side picture that is given over here, a thin sheet of lead is required to stop an X-ray, and then a several inches of lead is required for gamma rays. So that means gamma ray is the most destructive rays or ionization radiation that you can have out of the 4 alpha, beta, X-ray and gamma rays, right? Because it needs several inches of the lead, right? And it can penetrate paper, aluminum, thin sheet of lead that is mostly more than enough for alpha, beta and particle and X-rays. So let's take an example, whatever we learned on the ionization radiation till now, and let's try to solve this problem. Which of the following types of radiation, alpha, beta, gamma or X-ray, are stopped by a sheet of paper? Alpha particle, because of the size. A sheet of aluminum, we learned the beta particle, we need a sheet of aluminum, right? It cannot be stopped by a skin or a piece of paper. Then if you have a thick slab of lead, X-ray and gamma rays, skin, X-rays, because of the large size, skin can also stop alpha particle. Okay, so we are done for this chapter. So make sure you read the textbook and then follow the video, that whatever we learn in this PowerPoint, and that should be it. Bye.